pipe with a 1 centimeter wall thickness.
All right, let me just draw this first. So we're gonna get a cylindrical pipe on the z-axis. Always put the variables in. Don't put numbers in. Put variables until the very last step where you solve it. Because you're gonna be carrying numbers down, you're gonna make decimal point errors and stuff. So this radius, I'm gonna call A. And A is 10 centimeters?
Yeah, 1 centimeter.
Or 1 centimeter.
Mhm.
Go ahead.
And an inner radius of 4 centimeters is centered on the z-axis.
Whoa.
It's a pipe with thickness of 1 centimeter.
Oh, but the thickness is 1 centimeter. Sorry, so this is, and it's, give me, sorry, so the thickness, and let me use E for that, is 1 centimeter. It's centered on the z-axis, so it's a concentric pipe, right?
Mm-hmm.
And the thickness is 1 centimeter. What's the inner radius?
4 centimeters.
So this is 4 centimeters. I'll call this A equals 4 centimeters, which means B, the outer radius here, would be equal to A plus T, or 5 centimeters, right?
Mm-hmm.
All right, and what's the charge density in here?
3 coulombs of charge per meter.
3 coulombs per meter square. Whoa. This is
Per
a
meter
volume.
length of
What?
pipe. It says per meter length of pipe.
So 3 coulombs per meter, that's
Mhm.
not rho V, that's rho L. All right,
Rho,
cool.
yeah.
Mm-hmm.
Is evenly distributed in the pipe wall. Plot d rho as a function of radial distance from z-axis over the range of 0, which is less than or equal to rho, which is less than or equal to 10 centimeters.
All right, for this one, this is the classic kind of problem. What I'm gonna do is look right down the pipe. So I'm gonna come down the z-axis, and I'm gonna show you that there's the first, this is radius A, and then out here is radius B. And here's where the charge density, the volume charge density is that we have to calculate. When we do this problem, it's key to understand what's really going on. I know that if I take the integral of d dot ds over any closed surface, that's equal to the charge enclosed. And we know that. Now, the key thing with this one, first you establish the fact it is cylindrically symmetric. Do y'all agree with me there? By saying that, you also know that the D field is only in the radial direction. Do you agree with me? So we start off by saying, for this situation, there's 3 real conditions we have to take a look at. First, if we're inside rho equals A, if we say rho, that's the radial distance, is less than or equal to A, greater than 0, then our Gaussian surface is in here. We would have a can, you might say, that would look like it's this way. You all see what I'm talking about? With the height of that can, you always make h equal to 1. And now you can say within that can, the integral of d dot ds is equal to the charge enclosed. Well, how much charge is enclosed there? 0, right? Because the can the radius isn't large enough to actually cut into where the charge density is. So for this case, I know that the integral of d dot ds over the closed surface will be equal to 2 pi rho times the height, which is 1, times d rho, and it's equal to the charge enclosed. Well, the charge enclosed is 0, so that's the end of the story. D rho is 0 for that, period. And you don't worry about the top or bottom because the D field's in the radial direction, right? Correct, class?
Mm-hmm.
And the integral of d dot ds on the top of the can, if you think about this part, well, the ds is in this direction, rho is in that direction, so the dot product is 0. Does everybody understand this, class? Now we go into part 2. For rho greater than A, less than B. Now we're in the region where there is charge. And what we have to do is decipher what the volume charge density is. Do you follow me on this? Now he gives us how much charge there is per unit meter, right? What that means is if I have a unit meter from here to here, that's how much charge there is. But it's distributed over the volume from A to B, right? Y'all follow me? So if we take a height of 1 meter, we know there's 3 coulombs of charge evenly distributed within there. So we can say that Q inside that 1 meter height is 3 coulombs. Now how much volume is there? I'm going to try to draw this. Really what I have is this. I have a situation where I basically have a thick can, right? Correct, class? And what's the volume of that? Well, the simple way to do it is look down the can from the top, and you say it's inner radius A, outer radius B, right? What's the surface area right there of the top of that can? It would be pi b squared minus a squared, right? Pi b squared is just the entire area, right? As if it's radius b. Then you have to subtract out this inner chord. Do you agree with me? So that's the surface area, and then you multiply it by the height, right, that was distributed, which is 1, right? I said the height of this is 1. Y'all, is everybody following me on this? So that means the volume would be equal to simply height times this, pi times b squared minus a squared, or in a sense, the volume is just pi b squared minus a squared, right? And that means the volume charge density, I'm doing this wait, I don't mean to go that far down. The volume charge density would be the total charge, which is 3 coulombs, divided by the volume, which is pi, that's b squared minus a squared. So now I've got the volume charge density. Do you all agree with me there? Does everybody understand the method I've used to obtain it? Find the total charge in 1 meter. I know it's got to be evenly distributed over what volume? The volume of that thick can, or its thick pipe. Now we get into the thing about that part. Here, I look at this, and now I'm somewhere between, this is my radial distance, somewhere between A and B, right? Now I put my Gaussian surface, I'll try to draw here, but you'll forgive me. It's not drawn that well. I'll try to draw. So now what I'll do is this. Now I've got my Gaussian surface is somewhere, it's rho, it's between A and B, and it's a can like that, and it's got a height here. Always make H1 of H equals 1 meter, right? Now I write, always get used to rewriting Gauss's law. I know it gets boring. You go ahead and write the integral of d dot ds over the closed surface is equal to the integral of really the charge enclosed rho v dot dv. But that's only where rho v is non-zero. Right? Just write it generally. This is going to be always 2 pi rho times the height, which is 1, times just d rho. Does everybody agree that part of the integral is always going to be that? Right? It's just the perimeter times the height. We don't have to keep writing that over and over again and doing the integration, you know, the rho d phi dz, and then integrate over the limits. This is what it is. It's the surface area of the outer part of the can. On this side, it's going to be equal to what? Well, this is a volumetric integral, technically, right? And it's the charge density, which is equal to, I'm just going to leave it as rho v for now, rho v, because it's a constant. And the differential unit of volume in cylindrical coordinates is rho d phi, right? Then it's going to be d rho, and then it's dz. Does everybody agree with that? The differential unit of volume, rho d phi, that's the wiper arm tip movement. D rho, that's moving radially, and dz is vertically. It's a little chunk. Everybody agree with this? Real important when you see this. Now rho v is a constant. Now we set the limits, and this is the critical part. Where does rho vary from where the charge exists as non-zero?
From 0 to rho.
Ah, no, there's no charge in here, right?
Oh, that's right. So
We made rho v a constant, right? Where is rho v a non-zero value from where to where?
from A to B.
A to rho, right? Because remember, our can is somewhere between A and B. So it goes from 0 to rho, and technically I should prime these. Now I'm an engineer, I don't bother doing that in the real one. I mean, I know that this variable, this symbol can't be that symbol, but if it is, who cares? You're integrating that symbol out anyway. Yes, sir.
A to rho, right? Not
No,
zero.
no, I mean, I was from A to rho. That's supposed to be an A to rho, yes, thank you. All right, now, oh, sorry, that's a D, I put that where D phi is. It goes from A to rho here. Where does phi go from? I'm sorry, that was the first integration.
0 to 2 pi.
Does everybody agree with this, by the way? What I'm doing? And Z,
0 to H. Right?
or 0 to 1.
0 to 1.
Always leave H be 1. If you choose, if you have an option, it's always 1. 0 to 1. So really, this is the reason I'm saying that. Do we even need to bother with the DZ integration? That's another reason. So I don't even write it now. Just get rid of it. All right, now for the other integrations, All right, now I have rho v, that's a constant. When I integrate when I integrate d phi, I just get what, class? When I integrate d phi from 0 to 2 pi, I get
2 pi.
2 pi. And then when I integrate rho prime d rho prime from from a to rho d rho prime is rho prime squared over 2, right? And then you have to evaluate. So now it's going to be 1/2, and this is going to be rho squared minus a squared. And that's equal to 2 pi rho d rho, right? Now what I'm going to do is divide that by 2 pi rho to get d rho. So this is divided by 2 pi rho. Y'all agree with me here? I want to make sure everybody sees this. Got it, everyone? Y'all agree I can cancel the 2 pi without any problem, correct? So I'm going to do that. And that is an acceptable form. You can mess around with this all you want. If you want to divide by rho, this is going to be just rho, and this is a squared over rho. But this is an acceptable form right there for the answer. And you can put in rho v equals 3 over pi b squared minus a squared if you want. And if you did that, it would look like this. Then this would become 3. I can take the 2 out front here. And then I can simply divide this by b squared minus a squared. If you would like, you can do it that way. Do you agree with me, class? This is just putting a constant in there. We'll plot this in a second, but is everybody with me now? All right, the final part, that's between a and b. And finally, when we go from rho greater than b, call this equal to it. Then we have the integral, again, of d dot ds over the surface area is equal to, in this case, it's really going to be the charge enclosed. I'm going to leave it as Q enclosed. All right? Now, here's what I tell people. Always make the height of the can 1, right? Now my Gaussian surface is outside there, and it has an exact height of 1, correct, class? How much charge is in there? Just look up here. We're saying it's 3 coulombs per meter, right? H is 1 meter. How much charge? 3 coulombs without any mathematical operations at all. You can just say this is 3. It's that easy. Got it, guys? Because it's 3 coulombs per meter. If we go a height of 1 meter can, it's 3 coulombs, period, correct? Now, what is that equal to? What is this always going to be?
2 pi.
It's the surface area, 2
Yeah,
pi
2
rho
pi.
times the height, which is 1, right?
And then d.
Times d rho. And you can see, therefore, d rho is equal to 3 over 2 pi rho. And that's for rho greater than b. Are we with each other? Everybody got that? Now, it's important to see one of the things that happens here. The d field does not monotonically, it doesn't behave in a monotonic fashion. There are 3 changes, really 2 changes. So if we're going to graph the d field, if this, and I ask people to do this on tests all the time, quizzes, so you have to be able to graph things. One of the things you're going to do as engineers all the time, especially if you're in the field, you want to sketch out what you believe electric field signatures, D field signatures, B field signatures should look like, either versus distance or time. You want to give everybody an estimate of what he thinks should be there so they know what they're looking for. And it's important that you can sketch a mathematical equation somewhat accurately. I know that the real places to look are at A and B, correct? But this is radial distance rho. Do you all agree with me? Well, the value from 0, rho equals 0 to A is what?
0.
It's just 0, so there's nothing. Makes my life easy. Now, what happens from A to B? This is it right here, right? Agree, class? Here's the thing you take a look at. If you divide by rho, you're going to get a rho there, and then you're going to get an A squared by rho. This is going to have one of those kind of weird slopes where it does kind of this. It's going to start coming up, I believe, like this. Right there. It's sort of like a shark fin if you graph this. You can play with that. The reason I know this, I know the first term here is rho, right? Now, if it was just rho, it would be linear. But I'm subtracting from it an a squared over rho, right? And actually, I might have the bend on this wrong. It might be doing actually this. I didn't graph this, but it's probably doing that. Anyway, what it looks like is it's something that's increasing, monotonically increasing to this point. And at that point, it starts falling as 1 over rho squared. Follow me, class? And the max value will be at d or rho equal b. That will be the max value. If you want the max value, just come here and look. When rho is equal to b, you'll notice these two terms cancel, right? And then you have 3 over 2b be the maximum value of d rho. All right, class? Any questions about this problem? Just for completeness, what's the E field? The electric, say it.
Divide by sigma naught.
It's epsilon naught.
Sorry,
You
yeah.
divide by the permittivity of free space, epsilon naught, which is 8.854 times 10 to the minus 12, or 1 over 36 pi times 10 to the minus 9. And the units are farads per meter. You'll get used to that in time, okay? Any other questions about the homework? That's a good problem.
3.35. Or actually, no, 3.36. I just, my integration was different than what you had on there.
All right, let's, give me 1 second, we'll do it. Is this a sphere or a cylinder?
Sphere.
Good. Is it supposed to rain today, does anybody know? No. Okay. Good.
Oh, maybe it's supposed to.
All right, go ahead. What did you say?
So then maybe it's 30% chance at 1 o'clock, 50% at 2.
50?
At 2 o'clock, yeah.
See, I'm walking around campus at 2 to 3. Not looking forward to that. Go ahead.
Yeah. It says a thick-walled spherical shell with an inner radius of 2 centimeters and outer radius of 4 centimeters.
All right. That's not a very good show. A equals 2 centimeters, B equals 4 centimeters. Okay, go ahead.
Has an evenly distributed 12 nanocoulomb charge.
All right. So he's saying in there, there's 12 Q equals 12 nanocoulombs. Go ahead.
Plot dr as a function of radial distance from the origin over the range 0 is less than or equal to r, which is less than or equal to 10 centimeters.
Now, what he really wants is he wants to see how the D field changes versus radial distance, just like the prior one did, only now we're in spherical coordinates, we're not in cylindrical, right?
Mm-hmm.
Now, this is important. Let's get the charge density first. So I want the volume charge density in here, rho V. Rho V is always going to be the charge over the volume if it's evenly distributed. That's the charge density. Coulombs per meter cubed, right? Has to be. So he's given us the number of coulombs. Now what's the volume it's distributed over? It's this thick spherical shell, right? Well, the volume of a sphere, and you should need to know this, V of a sphere is equal to what? 4/3 pi r cubed, right? Where r is the radius of the sphere. Now, the way I always do these things is I don't write a differential unit of volume and do the integration because to me it's a waste of time. I know the answer, right? I take the volume of the outer sphere and I subtract the volume of the inner sphere to get the volume that's left over where the charge resides. Does that make sense to everybody? Okay, so now I can say the volume here is going to be 4/3 pi, and then it's going to be the outer radius, which is b squared, minus the inner radius a squared. So I've taken the volume of the outer sphere and I'm subtracting the volume of the inner sphere from it. I'm left with that region in between, A and B. Make sense to everyone, class? Now, I've got my volume. I've got the charge there, so therefore I have the volume charge density, rho V. I'm not gonna put in the values, but it's 12 nanocoulombs would go there. This would be equal to the volume. You divide charge by volume, you get the volume charge density. It is a constant in that region, so I don't even bother calculating it right now. Now the next thing I do is go through the three regions. First, I know that for R less than A, and you can say greater than 0, but that's implied. I know that the integral of d dot ds is equal, closed integral, is equal to the integral, or is really the charge enclosed. So the integral of d dot ds will be the surface area of a sphere, which is 4 pi r squared times the value of dr. Does everybody realize this is spherically symmetric and the only component of d you're worried about is the radial component? And that's equal to the charge enclosed. Well, how much charge is enclosed? Here's my Gaussian surface. I'm inside of A and I put a little sphere there. How much charge is inside it?
0.
Everybody see that? Right. I want to make sure everybody sees this. Well, if it's 0, then what's dr just by inspection?
0.
0 as well. Just like it was for the prior problem, the cylinder, right? Now the next part. Now for r greater than A, less than B. Remember, I don't put these values in yet. I put in just constants. Do all the calculations at the end if need be. You put in the values for the constants. Don't keep carrying those values through. Unless there's a really easy cancellation. It doesn't work well that way. Here, now when I'm between A and B, now my Gaussian surface, here's R, right? And now I put in my Gaussian surface here. And now I say the same thing, the integral of d dot ds over the closed surface is equal to the integral of rho v dv. That's the general statement. Now we put the specifics in. Well, what is d dot ds always going to be?
4 pi r squared.
It's always the surface area of the sphere, 4 pi r squared. Always, times dr. Here it's the volume charge density integrated. So now I'm going to put in the triple integral. I'm just going to put rho v here. I know rho v is a constant, right? And I'm only going to integrate over the region of space where rho v is not 0. Not where rho v is 0. Makes no sense because then it would be 0 times something. So here I put in my differential unit of volume. How many remember first? Did you do this one? Do you know what the differential unit of volume is for spherical quartz?
Is it r squared dr sine theta d theta?
Yeah, you're right. R squared times sine theta times d theta, d phi, dr. It doesn't matter the order you put these in. Okay, I chose to do it this way. Now we have to be careful. So theta goes from where to where?
It goes from 0 to pi.
That's right. 0 to pi. Phi, on the other hand, goes from where to where?
0 to 2 pi.
And R?
Goes from A to B.
A to R.
A to R, okay.
Right, that's a common mistake, A to R.
Yeah, I might be wrong this time.
Because we just want, remember, we're looking for the D field anywhere between A and B, therefore it's a function of R. Okay? Now when you do this, what does this integration become? I'm just going to put the 1 over 4 pi r squared there and dr here. I know I'm going to divide by that. Well, when I do the integral, first of all, sine theta d theta integrate, right? That's minus cosine theta. When you evaluate that from 0 to pi, you get 2. You can do it. I've done this so many times. 2. Now, when you integrate d phi from 0 to 2 pi, you get 2 pi. There's nothing, it's a function of phi in there except d phi. So it's going to be 2 pi. So that means this becomes 4 pi, essentially, right? 2 times 2 pi is 4 pi. Now we integrate rho squared dr, which we get is
R cubed minus A cubed.
r cubed over 3, right? So, and we evaluate it. So we get r cubed over 3, and I want to put this down. We evaluate it from A to R. Now, I'm putting that down there for a reason. I want to show you how, when you look at this right now, the integration, do you all see how the 4 pi's cancel? Class? And you all see right there,
2 R's.
what's that?
2 of the R's canceled.
Well, no, I remember you gotta evaluate this.
Okay.
Yeah, so be careful about that. This you have to evaluate. So I'm gonna say that D of R right here is equal to 1 over R squared, because the 4 pi's cancel, divided by 3. And then I evaluate this, R cubed, at R, which is R cubed minus A cubed. And that's my D of R. Do you all agree with me here? And that's between A and B. It's very similar to the prior one, right? Only thing, the geometry, or the system of, it's spherical, not cylindrical symmetry, so the differential volume is different. Now, we go out here finally and we say for R greater than B, we want to know what dr is. Make that equal to. Then I think you can do that. So now, integral of d dot ds over the closed surface equal to the charge enclosed, right? Well, this is going to be what? The integral of d dot ds is always spherical coordinates? 4 pi r squared d of r, right? So put it as 4 pi r squared times dr. That's always the case. How much charge is enclosed? All right, think about it. Now we're outside B, right? So when we put a spherical surface around there, how much charge is enclosed? All of it, right? All of it, 12 nanocoulombs. So here, we just know it's Q, 12 nanocoulombs. Or therefore, d of r is equal to Q over 4 pi r squared. And that's what it is. So now we have it and we have to graph it. Okay? Did you do this one? Do you have graphing calculators?
Yeah.
Can you put in multiple, can you define d over multiple functions for a graph or not? I'm asking this because I don't know.
Never tried.
All right, because you have, really you have 3. The one you have to worry about is right here. The other 2 are easy. So if we take a look at this, if this is A and this is B and this is radial distance R and this is D of R here, well, from 0 to A, what's the value?
0.
It's just 0, just like the last one, right? Remember, if you don't enclose any charge and it's spherically symmetric or cylindrically symmetric, it's 0. Now between A and B, what do we have? That guy, right? Can you plot this guy on your calculators easily? Because I think it does. Let me see. I think it does this. I think it's got an upward loop to it, I'm almost positive. And then at B, it'll start coming down like this. And this is the max value. And it would occur at R equals B. I don't know if you can get it, but it should have a little, like a bend upward. You have graph? Josh, you have graph on yours or not?
Yeah, I'm trying to figure out how to do like the piecewise stuff.
Don't worry about piecewise, just graph that one part. The other parts are easy.
I mean,
If you do just the 1 over 3 r squared times r cubed minus, and you can put a constant for A, just put down.
Here's the, when you posted the graph, if you want to look at it.
It's got it bending the other way. Okay. Then I'm wrong on this one. It bends the other way. It's a shark fin. The way you can find out is I can take a derivative of that, and then see how the slope varies. And it looks like it's a decreasing slope. I'm just gonna accept that as fact. You all agree with me here? How do you get the E field from this?
Divided by epsilon.
Remember that. All right. Any other questions? That's a good problem. Guys? All right, I'm going to throw one thing out here, so we all together, because this is kind of a difficult thing. These are good problems, and they showcase really Gauss's law. Now, you realize if you did this thing where you took a differential chunk of charge and defined a differential E field and did that integration, that would be a nightmare. I'm just saying that. It's a pain in the butt to do that integration. It's in spherical coordinates, it's a vector thing. But this Gauss law makes it simple, trivial, compared to the integration. some of your calculators, I think the TI 89 and 93, you can actually get cards or modules for certain types of things like chemistry, physics. I don't know if they have one for electrical and computer engineering, but they might, where they have all the constants and things that are commonly used. I'm just saying that it's kind of nice if they have that available. Anyway, are there any other questions about Gauss's law? Because this is the problem I'm going to ask you how you would do. This is kind of a typical quiz problem. So if I start and I say, I have a radius A, and inside here I have a volume charge density of 3 over R coulombs per meter cubed. Inside. This would be for R less than A, less than or equal to A, greater than or equal to 0. And rho V is 0 else. And I want you to plot the D field versus position. So I'm looking for D of R first, and then I want to know what it looks versus position. How would you go about doing this? Please just comment. I'm looking for interaction.
This is a sphere.
Yep, spherical coordinates.
You start with Gauss's law.
Well, yeah, good point. And actually start with what region you're going to be talking about. So how about R less than A, okay? That means inside the sphere. You have to do that, all right? Now, you're with me? Keep going. I'll state it, integral of D dot ds, closed surface is the integral of rho V dV over the volume. Now what is D dot ds?
4 pi r squared dr.
That's correct. Now what is this going to be? It's really a triple integral, right? And it would be rho V, which is 3 over R, correct? Now what's the differential unit of volume in spherical coordinates?
R squared sine theta.
It's going to be R squared sine theta. Go ahead.
D theta d phi dr.
Yeah, it doesn't matter the order. And where does theta go from?
0 to pi.
Phi?
0 to 2 pi.
R?
0 to r.
Right, 0 to R. Technically, we should prime these guys, right? All right, now, one thing you see is something, yes.
Can you leave rho V, just rho V, or do you want us to?
Well, I put, well, no, see, it's a function of R.
Okay, okay.
All right, so it's not a constant, that's my point. It's a function of R, so there's gonna be cancellation. Okay. You all see this? Oh, so what cancels here?
R prime on bottom and r squared.
Right, so it goes to just R prime here. With me? Now, when you do this, I can see the D of R here. You're absolutely right about this. It's going to be 1 over 4 pi R squared. Now, when I do the integrations, I can see D phi and D theta are going to give me 4 pi. Just get used to that. When I integrate sine theta d theta, it's minus cosine theta, evaluated from 0 to pi will give me 2 all the time. When I integrate d phi from 0 to 2 pi, it's 2 pi. So I have 2 times 2 pi or 4 pi. I know I'm going to have that. Now, when I integrate dr, r prime dr, I get r prime squared over 2. Evaluated from 0 to r is just going to be r squared over 2. Do you all agree with that? Because when it's 0, it doesn't matter, correct? We don't have a shell here. We have something that starts at 0. And what do you notice happening?
4 pi's canceled.
And r squared is correct. What do you notice that's rather unique?
It's a constant.
D is a constant, right? It's a constant out to where? A, right. Now what happens when R is greater than A? When R is greater than A, always write integral of D dot ds over the closed surface is really the charge enclosed. Here, how much charge is enclosed? All of it, right? So you have to do the volumetric integral theoretically of integrating that rho v over the entire volume, correct class? We'll do that in a second. But it's the total charge enclosed. And what is this going to be?
4 pi r squared d.
That's right, 4 pi r squared d of r. So I can say d of r is equal to 1 over 4 pi R squared times the charge enclosed. Well, the charge enclosed will be the triple integral of, in my case, rho v, which is 3 over R, times the differential unit of volume, R squared sine theta d phi dr. Here, I know that theta goes from 0 to pi, phi goes from 0 to 2 pi, and R goes from 0 to where? A, right. And that's it. So what is d of R? It's 1 over 4 pi R squared, and then it's going to be times 4 pi, right? And look, that goes, and I have R squared dr, right? I mean, I have R dr, which is R squared over 2, correct? Makes it A squared over 2, right? And here the 4 pi's go, but then you see d of R is equal to A over R squared times 1/2. Does everybody see that?
I think you left the 3's out of the one.
I did. And this should be, it's right there, but it's not here. You're absolutely right. And this should have a 3 too. I'm sorry about that. You're absolutely right. Are you with me, class? Now, what does it look like if you graphed it? D of R here versus, not the A, it would just be a constant, right? And then from here, it would start falling off like that. And that would be it. Now, these are the kind of problems, think of this problem, make it a little more complex. Say the charge density that I give you only exists between A and B. Sure, you can inner radius and an outer radius and do it. But that's sort of the level of complexity you can expect on quizzes and tests with the Gauss's law problem. Either cylindrical or spherical coordinates. I do not give you problems that are absolutely nutso integrals. I just don't. It doesn't really serve the purposes of this class. You're trying to teach really concepts, and you're trying to get people acquainted with how the mathematical statements of the physical laws are really assessed for things like this. Everybody okay with this? All right, we're done with Gauss's law then, unless there's any other questions. Now, at least the integration part. There's a differential form of Gauss's law too. Did I give you any problems that required the use of div d or not? I don't think I did, but I stated what div d was last time. I know that, right? The divergence of d, remember? I said Gauss's law had 2 forms. It had an integral form. Let me go through and state it again. Now, just hear me now. How many remember this stuff in physics? Right, if you've had a good physics background, then this is second nature to you. And when I was sitting where you were, I had a really good physics teacher, and we used a book by named Tipler. The best physics book is probably Holliday and Resnick, but I don't know which book they use here right now. But I remember I did every odd problem because it had the answers, and there were like 50 to 100 problems in the back. And working problems was the key to really understanding this. You worked on as many problems as you could. I'd spend 3-4 hours a night sometimes. Whenever we do these things, that way you were completely comfortable with any type of problem given. You just had it down because you saw everything by that time. So, when I came from that background, this stuff was second nature. I didn't worry about it when I was taking EMAG because I already had, there's things coming up I never had before. But this is relatively second nature. Now, this is the divergence form. I don't know if you got this in physics. Remember, the integral form of Gauss's law says the integral of d dot ds over a closed surface is equal to the integral of really rho v dv over the volume on a Gaussian surface. Gauss's law is always used in highly symmetric cases. There's also something, and this comes from a mathematical theorem. It's called the divergence theorem. It's the integral over a surface of a vector. I'm going to use d dot ds. So if you integrate a vector over a surface, a closed surface, this is the same thing as integrating, and it's a triplet. This is normally a double integral. This would be a triple integral over the closed surface of the divergence of d dv. Now, divergence of d, just look up here, is equal to the volume charge density. This is the divergence form of Gauss's law, or the differential form. You follow me on that? Now, the divergence of d in Cartesian coordinates is just d dx dx plus d dy dy plus d dz dz. It is a scalar operator. So the result of a divergence is a scalar, not a vector. If I take divergence of d in spherical or in cylindrical coordinates, it's 1 over rho d rho of rho times d rho. You can look in the back of the book, plus 1 over rho d phi of d phi plus, and this is going to be just dz dz. And that's on the back cover of your book. If you look at the very back of your book, on the upper left-hand corner has the divergence operator. Now, I will not give you the Cartesian coordinate one, because this is obvious, you should know this. It's just 3 derivatives with respect to the x component of d, the y component of d, and the z component. This one I'd give you. You're not used to that yet. After you get used to it, I don't. And I'll also give you the spherical one. The spherical one's a little different. It's divergence of d. Look in your book. And there's a couple forms of this. It's 1 over r squared times d dr, and this is going to be r squared d of r. He has it this way, doesn't he? He has it 1 over r squared d dr of r squared times d of r, or whatever.
It is r squared ar, but yeah.
Well, he uses a for the symbol here, doesn't he? Instead of d. A is just a vector symbol. Then he's going to have plus 1 over r sine theta, and this is going to be d phi here, and it's going to be of the way he has it, I believe it's going to be, this is going to be r, is it r d, or does he have r d phi in his?
No.
What?
He had 1 over r sine theta d theta.
Oh, he's got theta first, sorry, all right. I put phi first, so d theta, and then it's going to be of r d theta. Does he have this form?
He's got d theta sine theta.
Ah, okay, never mind. I'm wrong there. So this is going to be d theta of sine theta d theta, right?
Mm-hmm.
My bad. And this is going to be, the last part is 1 over r sine theta, and then it's going to be d phi here. And here he's going to have d phi. Is that right?
Yeah.
All right. There's a couple different forms. Normally, the way you do these things, because when ordered pairs are r comma, and then it's theta for spherical coordinates, and then phi. The first derivative is with respect to r. The second derivative is with respect to theta. The third is with respect to phi. Let me make mention of one thing. If you look here, can you see how this can be expanded? If I have 1 over r squared, leave it alone. If I take d dr of this, I could get 2r, right? Times d of r plus r squared times d dr, right? D of the differential of d of r with respect to r. Sometimes that part's expanded, but this is a more compact way of writing it. So these are the differential operators. Now we'll do one problem in the book that relates to this. Let me just take a look. This is chapter 3. And see, I don't spend much time on this because this is just a mathematical operation. It's a no-brainer. If you're given the D field, you simply do these operations to get rho V. And if you want the charge density, you can either integrate, or the amount of charge in a region, you can either integrate the integral of d dot ds over a surface to get the charge in the region, or you can take the divergence of d and integrate it dv over the volume. Either one will get you. So here, this is in section 3.8. Why don't you, looking for a tougher one. Why don't you read 340 to me? Problem 340.
Suppose vector D equals 6 rho cosine B AB joules per meter squared. Then A, determine the charge density at the point 3 meters, 90 degrees, and then negative 2 meters. Find the total flux through the surface of a quartered cylinder.
All right, we're gonna do this first part. The whole thing about this is, if they want rho v, you take a divergence. Understand everyone? So the divergence here, this is cylindrical coordinates, right? The only component I have is the phi component. There is no there is no rho or z component. So if you look at the definition here, it's 1 over rho d phi, right, which is gonna be that right there, 6 rho cosine phi, d phi, take a derivative of that. So that means rho v here is equal to 1 over rho d phi of this, of 6 rho cosine phi, and it's coulombs per meter. Do y'all see what I'm doing here? I'm just executing the definition. I'm applying it. Now, one thing to take, just by looking at this thing, what happens to the rows? Rows cancel right away, they cancel. So I'm left with it 6, right, times the derivative of cosine, which is
Negative sign.
minus sine of phi. That means rho v is only a function of the angle phi. The value of z and rho don't matter here. Follow me? So they asked to evaluate rho v at this point. The only thing you care about is the 90 degrees. Do you see that? And that means the value is minus 6, right? Sine of 90 is 1, right? So minus 6 would be equal, 6 coulombs would be the value of rho v there. Z doesn't matter and rho doesn't matter. Agreed, everyone? I don't know if he has an answer in the back, but the solution manual for this is everywhere. I assume several of you have it by now, and it doesn't bother me in the least. I think it can be useful if it's applied correctly. You first struggle with the problems, then you look and see if your answer matches theirs, and if not, you find out why not. But you always take a crack at the problems first by yourself. Don't look at a solutions manual until you try and see if your answer jives with theirs. Is this right?
Let me see.
It's problem 340.
Yeah, it says, yeah, negative 6 sine theta. Yeah, so negative 6.
All right. Next, what did they ask for the charge where?
This is find the total flux through the surface of the quartered cylinder defined by rho is less than 0, or greater than 0 and less than 4 meters.
All right, so he's going from 0 to A, and A is 4 meters. Go ahead. Go ahead.
And then phi is from 0 to 90.
All right, so that means this is phi. If this is X and this is Y, phi is the measurement in the XY planes from 0 to 90 would be this. Is this a can or it's a cylinder, right? Quarter cylinder?
Mm.
And the height is where?
From negative 4 to 0.
No, negative 4. So he's so negative 4 to 0. So really he takes a can and he cuts everything out except a quarter of the can that has a height from minus, is it minus 4?
Yes, sir.
So I'm gonna call this down here H, and H is minus 4 to 0. Well, you can do this 2 ways. I want you to hear me. You see how the D field right here is in the phi direction, right? So if you look at this, the only surface integral that would be non-zero, since this is the phi direction, the differential surface here would be A phi times dz, right, times d rho. Do you all see that? That would be the differential surface right here on this side. The differential surface here on this side, that would be minus A phi. The differential surface here on this side would be plus A phi, and it would be dz, and it would also be d rho. This surface right here is minus A phi dz d rho. D rho. Can y'all understand what I'm doing here? I'm just taking this flat surface there, that's the differential surface there, that's the differential surface there. Now, examine what the D field is, because if we do the integral of D dot ds, we have to multiply that differential surface vector with the D field and then integrate it over the surface. But take a look at this. Well, when phi is 0, isn't that phi 0 right here? On the x-axis, right? When phi is 0, the cosine is 1, correct? So we'd be integrating 6 rho, d rho, dz over the proper boundaries, right? Out here, what's the value of phi out here on the y-axis? How far did it go from 0 to?
90 degrees.
It's 90 degrees, isn't it? Right? And if you're not catching on to this, just follow me. If I look down the z-axis, and this is x and y, remember, any radial distance rho, this is the angle phi I'm talking about. So if you're on the x-axis, you're at phi equals 0. If you're on the y, you're at phi equal 90, positive y-axis. Everybody got that? Now, at 90 degrees, what's the cosine of 90? Y'all see it 0?
Mhm.
So what we could do is just integrate that D field over that surface, right there, at x equals, this would be on the x, in the x z plane at really phi equals 0. You're basically integrating just over that surface. Can everybody visualize this? And what would that integral be? Well, I could say that the total flux, which is the integral of d dot ds, now when he says total flux, I think he uses this symbol. Total flux is nothing more than charge enclosed. That's all it is. So I always use the word charge enclosed. So the integral of d dot ds here would only be the integral of the D field over that region. And that means it would be the integral, it would be a double integral of the D field, 6 rho, times cosine phi, times a phi, times the differential surface right here. Can you all see the differential surface has a differential height, dz, and it has a differential radial thickness, d rho, right? And it's in the minus a phi direction. You all see that? Now, what are the limits? Where does rho go from? 0 to a, right. And, sorry, yeah, that's the outer one. 0 to a. And where does z go from? Minus 4, I'll just put that, yeah. I can put down minus 4 here to 0. Normally I don't, but now what happens here? Well, if I have a phi dot a phi, I get 1, right? But I have a minus sign, that comes out, so I have minus, then I can take the 6 outside. Now, when I integrate dz from minus 4 to 0, what do I get? Well, I get z evaluated from minus 4 to 0 or 4, don't I, class? So it's times 4, minus 6 times 4. Then I integrate, oh, by the way, what's the cosine of phi's value here? 1, right? Because we're at phi equals 0, correct, class? So I can, for all intents and purposes, just get rid of that. Now, when I integrate d rho here times rho, I get rho squared over 2 from 0 to a, or I get a squared over 2. And that means I have minus 6 times, really I have minus 6 times 2, or minus 12 a squared, and the outer radius is 4 meters, right? So it's 4 squared, so that's going to be minus 12 times 16, correct, class? Is that the answer there, Hannah?
Yeah, minus 192 coulombs.
Oh, minus 192 coulombs. Now that's using a surface integral, right? However, since this is the volume charge density, we could get the same exact result, and it doesn't matter which one you use. We can get the same exact result by doing, you can say the charge enclosed, which is equal to the flux. He uses the symbol from flux. It's the same thing. Total flux is equal, if you say the total flux coming out of region is charge enclosed, but you can have flux just through one surface. Then you can say that this is equal to the volume charge density, which is here, integrated over the regions, which is going to be, I can put the 6 out here, and I can put the minus sign. It's sine of phi, right? And what's the differential unit of volume in cylindrical coordinates? Does anybody know? Cylindrical. It's always gonna be what? Rho d phi, that's the wiper arm tip moving, right? Then it's gonna be, and then, right, always that. The order is, it doesn't matter. You can put phi first, rho first, whatever you prefer. So now we put the definition down. Remember, this is just a quarter of a cylinder. So when we say where phi goes from, where does it go from?
0 to 90.
Does everybody see that? Or pi over 2? 0 to 90 degrees or pi over 2. Where does z go from?
-4 to 0.
-4 to 0. And where does rho go from?
0 to 8.
Right, and I'm mixing things. I should put a constant there, but I didn't. So what does this come down to? Well, when we do this, if we integrate sine of phi, right, I get cosine of phi, don't I?
Minus cosine.
Minus cosine of phi, I'm sorry, minus cosine of phi. And when I take minus cosine of phi, let me just do this, minus cosine of phi, and I evaluate it at 90 degrees, that's 0, is it? So then I have minus cosine of phi minus, which makes it plus, cosine of 0, which is 1, right. So when we do the sine integration from 0 to 90, we get 1. Now, when we integrate dz from -4 to 0, what do we get?
4.
It's just the height, 4, yeah. We get 4, right? I know there's a minus, let me put this -6 in front of there, so it's -6 times 4. And then we finally integrate rho d rho, and that's rho squared over 2 between 0 and a, which is a squared over 2, and it's the exact same thing we got here. It just proves a point, or it enforces the concept. Understand, class? So it doesn't matter if I asked you to find the total charge inside there. You could take the divergence of d and do the integration, or you could simply integrate d dot ds over that surface and that surface. And since this integral is going to be 0, it's really only on one surface. They're the same exact value. Everybody got that?
So you only do those two surfaces because it's in the a phi direction, right?
Absolutely. Remember, the differential surface is always perpendicular to the plane of the surface. This plane is in the rho z direction, right? Therefore, it's a phi, but the vector's pointing outward, which would be positive a phi. A phi is a vector pointing this way. It's, if you take a look at the tip, if this is down the z-axis, a phi is this way. That way, if it's pointing that way, it's minus a phi, and that's important. Okay? Here, it's plus a phi, here it's minus a phi. All right? It's real important to catch that. All right, we good on this? I'll give you some problems with that. Now I'm going to cover voltage. Probably one of the terms that you've heard a lot about already because you've taken your circuits course, right? You've taken either Dave Irwin or somebody, and you've talked about voltage. How was voltage explained to you before in physics or in Dave's class? Remember? Electrical pressure. It's really what we think of as atmospheric pressure has an analog to electrical pressure. Pressure by itself doesn't mean air is flowing. The only way air flows is if there's a differential pressure between 2 points, and there's some way the air can move. In other words, if there's not a plate between them. And that's my analogy to air moving is really current. So now we're going to get into what voltage really is, and this is from a physics concept. You've had this. If you've had a good physics teacher and you've spent your time doing the homework, you probably really understand voltage. But voltage really has to do with work, and it has to do with work an outside force does. So first, let me just get into the force business. When we talk about force in general, if we integrate force over a distance, dl, right, from any point A to B, That's really the work that's involved with moving something from A to B, or it's the energy that's required to move that, or that's related to the movement of that from A to B. Correct, class? I'm using E for energy. So we know that. Well, if you have an electric field and a charge Q, put a charge Q here, and just say there's an electric field E. Now this is the electric field that's going to be static, it's impressed there. It's everywhere in the same direction, same value. If I integrate the integral of the force here on this charge first, the force would be equal to Q times E, and that would be a vector. Do you all agree with that? So it'd be Q times E, or Q times E, and that's the force that would be here, and it's dotted with dl. And I'm gonna go from A to B. Well, that's the work that the field does to move something between point A and B. And you always put the upper limits first, the lower limits behind it. So that's the work or the energy that the field would require to, would really do, moving that charge from these 2 points. Now, when we talk about voltage, we don't talk about the amount of work or the force, or really the work involved in the field moving it. It's how much work I would do to move that against the field, that amount. In other words, if this is the amount of work the field would do, then how much would it take me to get the thing back to its original position? It would be minus that. Do you follow me on this, class? So first we take this, and we take the work B to A that the field does, and we divide it by Q. And then we put a negative sign, and this is equal to the voltage between B and A. So the voltage between B and A is the electrical pressure, and it's really amounts to how much work I did moving something. For instance, if I had an external field in this direction, say it's 1 volt per meter in that direction, just say it's horizontal, and I got to charge 1 coulomb here, all right? And if I move it from this point, call it A, to this point B, so now I move it. Now you'll notice I'm moving against the field. The field's pushing it this way, right? The work I would do in moving that would be positive work. I'm pushing against the force, so it means I'm applying a force that's, when I integrate that force, it's in that direction from here to here, it's positive, right? And if I divide by the charge, that would be the voltage between these 2 points, where this would be VAB, where this would be A, and this would be B. And by the way, VAB, or VBA, is really equal to VB, mark this down, minus VA. And this will give you some insight. It's like putting the plus lead of your meter there, and the minus lead, or the negative part of your meter there. So if you have a little volt-ohm meter, back in the old days when they were analog, and you took the positive terminal and you stuck it right, you would stick it right there, and the negative terminal, and you would stick it wherever A is. Does that make sense to you? That's how the voltage would be measured. So now we get into calculating the voltage for some typical distributions, and I'm going to give you some insight as best I can about how I think about this. First, we start with just a point charge. Now, one thing about voltage too, it's a scalar. That's one thing that's beautiful about it. It's a scalar, not a vector. But yet, if we have an equation for the voltage, we can obtain an equation for the E field. I'm going to give this to you right now. It comes a little later, but you can define the E field, and this is for the electrostatic E field, is nothing more than minus the gradient of the voltage. I'll write that down for electrostatics. The gradient operator is also in your back of your cover of your book, and if you look back here, this comes a little later. That's the second thing that they talk about, the gradient operator. And that's nice, but you'll see how nice it is in a second. So, and well, a little bit. So first, let's calculate the voltage for a very common distribution. Let's say I just have a charge, better get a point charge. I have a point charge here, Q. And I have a radius A and a radius B. Here, B is assumed greater than A. And I want to calculate VBA, and I want to know what it is. Now, here's the thing I'm going to tell you. The closer you get to a point charge, if it's plus, the higher the potential is, the higher the voltage is. Potential, electric potential and voltage are interchangeable. They mean the same thing. You understand that? So the closer you get, the greater the value of voltage is with respect to anything. They always say it's with respect to a ground because A is what I show you the negative terminal. You know how that's called common or ground usually? So the voltage at B, right here, is always with respect to A. Now the closer you get, the greater the value is, right? That means at this distance A, it would have a larger value of voltage with respect to anything than this voltage here, right? That makes sense to everybody? So if I put my positive lead here and my negative lead here, I would read a positive voltage. But if I put my positive lead where B is and my negative lead here where A is, I would read a negative voltage. Does that make sense? Please try to understand. I am trying to give you insight, the way I think about these. So let's calculate it formally. So I said VBA was equal to, right here, minus the integral from A to B of the E field. Now, that's the next part. This is a point charge. You might as well put it at the origin, all right? By the way, for this system, doesn't spherical coordinates make sense? If we got one point charge at the origin, sure, spherical coordinates. That means the E field anywhere, at any given radial distance, would be given as Q over 4 pi epsilon naught R squared AR. You all remember that? So I put down the electric field. It's Q over 4 pi epsilon naught R squared AR. Now I've got to dot that into a differential length. Some of you know this, some of you don't. In his chapter, and I think didn't I include a post thing where it has the differential links or not? I didn't. Let me make a note of this to do it. I'm going to show. Add, really, coordinate system and differentials. And I'll post this because it'll help you. I guess I didn't do it, but I did talk about this and we went through the differential surfaces, the differential volumes, right? Well, differential length in spherical coordinates is just the differentials with respect to the axis. So dl in Cartesian would be dx ax plus dy ay plus dz az. In cylindrical coordinates, dl would be equal to, here it's going to be d rho a rho plus, and then it's going to be rho d phi a phi plus dz az. Now you can see what's happening here. I'm just taking the differential sides of the volume and putting them as the respective differentials multiplied by what their actual, what the differentials, this is rho here, that looks like a phi, but it's supposed to be a rho. So that's rho, phi, and z, okay? I think I put this up once. And then for dl, if it's in spherical coordinates, what is it? It's dr, right? Then it's going to be plus, think about the wiper arm, it's r sine theta, right? D phi, a phi, right? And then it's, actually this one should be last in the order of things. This should be r sine theta, d phi, a phi is the last one, and this middle one is going to be r, it's going to be r times d theta, a theta, but that's the differential in spherical coordinates, differential length. This, and this are the edges of the cube, the differential volume. If you're not real familiar with this, it'll take a little time. So now, when I take this differential and I put it here, and I'm doing it only one time, I have what? dr AR, right? Plus, what's the next term? R d theta, what? A theta, and the last term, R sine theta d phi a phi, right? I'll only write this once. That's the DL in spherical coordinates. But what do you really notice about this? What is AR dot A theta? It's 0, they're orthogonal, right? What is AR dot A phi? 0. AR dot AR is 1. It's the only one you care about. So usually I don't even add those other differentials. I only know that that's the only one that's going to matter for the differential length. And AR dot AR is 1. So I get this. Now that means I have VB minus VA equal to minus Q over 4 pi epsilon naught. And here, what is 1 over R squared dr integrated? It's what? It's going to be minus 1 over R, right? So I have minus 1 over R evaluated from B to A. You'll notice there's 2 minus signs. So now I have this equal to Q over 4 pi epsilon naught times 1 over B minus 1 over A. Now what do you notice about that? If Q is positive, what do you notice about this value because I made B greater than A? 1 over something greater than something less is, this is going to be smaller than this, right? So it's negative. Do you all see that? So that's calculating the voltage between 2 points in spherical coordinates from a point charge, or a known clump of charge centered at the origin. I've got 13 after. I don't know if that's right or not. All right, now, the next thing we're going to do, you can almost guess, if I've done spherical, probably cylindrical, right? Probably cylindrical. And people mess up the sign on this stuff all the time. Sign is important here. So the next thing is this. Now I have just a line of charge, that we are charge density, rho L. Let's put it on the z-axis. And now I want the voltage difference between 2 points. I want you to follow me on this one. This one gets a little interesting. So I'm going to come out a distance A, and this is distance B. And I want to know what VBA is, and I'll give you that A is going to be less than B. And I want to know what the value is. So how do I do it? Well, first you have to know what the electric field is from the charge distribution you're talking about, right? What's the electric field from an infinite line charge? Do you remember? Anyone? You gotta know this one for Friday. Rho L over 2 pi epsilon naught divided by rho, well, radial distance rho, in the A rho direction, right? And that A rho has a very unique meaning. It means radially away from the line charge, right? It doesn't mean from the z-axis always. It means where the line charge is. So A rho could, in a sense, have an AXAY value or something like that. Understand, class? So at least for this system, that's what it is. Now, what's the differential length in cylindrical coordinates? Well, it's equal to simply d rho a rho plus rho d phi a phi plus dz a z. That's the differential length. When I go to get VAB, I say it's minus the integral, right, from A to B of the electric field, rho L over 2 pi epsilon naught rho A rho, dotted with DL. Question, do I need to include these two last things? Why not? The dot product makes them 0, right? So I only include the first part. Rho, it's going to be d rho A rho. And here you can see A rho dots out, right? 1. And and now I'm over. And when you do this integration, what do you see you get? You get minus rho L over 2 pi epsilon naught. And then it's gonna be times what? What's the integral of 1 over rho, class?
log of.
Natural log of,
Rho.
in this case, it's gonna be B over A, right? But that minus sign would allow us to flip and put it A over B, wouldn't it, class? And this is the way it is. I want you to take note of one thing, though. What is the voltage going to be in terms of its magnitude if B goes to infinity, holding A finite? What's the log of infinity? Infinity. In other words, when you have an infinite line charge, as a matter of fact, any infinite charge system, anytime you take the difference between a distance close by and then an infinite distance from that charge, it will tend to infinity in magnitude. Now, Larry, follow me? Just keep that in mind. There are no infinite line charge distributions, but if you get close enough to something, like if you're 1 inch from a power line that's maybe hundreds of feet long, it looks pretty much like an infinite line charge, or an infinite line at least, if the charge density is constant. All right, I'm gonna give you some problems on that. For Friday, the quiz is gonna be on the last 2 homeworks in today. All right, so it's kind of one of these things, electric field, voltage, kind of things from systems, okay? I didn't have time to get to the gradient operator to calculate the electric field, but we'll get there Friday. And if you have questions, I'm available now.